Ladies and gentlemen, let's continue with chapter 9 on natural convection. We are going to finish the chapter today. We are following the textbook of Cengel and Ghajar, and it's edition 5. What we've already done in this, what we've already addressed in this chapter is firstly the physical mechanism of natural convection, the equation of motion and the Grashof number, natural convection from different types of surfaces, and there we've looked at vertical plates, inclined plates, horizontal plates, and horizontal cylinders and spheres. Then paragraph 9.4, natural convection from fin surfaces, typically from electronic components with different types of fins. We didn't look at it in detail, also not the next part, paragraph 9.5, natural convection inside enclosures, because there are many different types. There are horizontal rectangular enclosures, inclined rectangular enclosures, concentric cylinders, concentric spheres, etc. So we didn't have enough time to go through all of them in detail. However, the very important thing is it is all about the Nusselt number as a function of the Grashof and Prandtl number, and we have to get the Nusselt number from equations or tables or graphs, and very important, read the fine print and then just apply the fundamentals. The last part that we're going to do today is paragraph 9.6, which is the combined natural and forced convection, and it is also, I don't think it is being addressed or called like that in this textbook, but it is also called mixed convection, and I think for good reason. Just going back to what I've said so many times previously, the Nusselt number is a function of the Reynolds number, the Prandtl number, and the Grashof number. With chapters 6, 7, and 8, the Reynolds number was the driving force. That was by far the most important influence, and the Grashof number was negligible. So these were chapters 6, 7, and 8. And then in chapter 9, the first part up to from 9.1 to 9.5, this one was the most important one, and the Reynolds number was negligible. So in paragraph 9.6, these two now, both of them combined, are very important, and we cannot neglect one of the two. Showing it with an example, let's look at vertical flow over a heated plate. So this is a heated plate, and we've already looked at the fact that we're going to have buoyancy forces, and the result of that is that we're going to have a thermal boundary layer with a certain, let's call it an average velocity. And that arrow length I'm using there is an indication of the velocity. Okay. So if we just heat the plate in a vertical configuration and there's gravity, then that is what is going to happen. Now, with that same plate, what I'm going to do now is I'm putting a small fan there. And you see it's small. And if we now look at this same situation with the same heated plate, my velocity vectors, I'm going to draw them a little bit larger now. Do you agree? I mean, the average velocity is going to increase because the fan is assisting, it is helping this natural convection. So there's my fan. Okay. Then the third situation is I've got a big fan. Okay. And now, obviously, the velocity is going to be much larger. So what we see here is that in this case we've got assisting type of mixed convection, and I'm going to describe that a little bit later. We can also have the opposite. Let's look at this plate, which is now being cooled. Okay, it's a cold plate. What is now going to happen is the flow is going to flow downwards because the density As the temperature decreases, the density increases, and therefore it goes down. So in this case, if we just cool the plate, the average velocity is going to look something like that. If I would now put the small fan here, the small fan, it would mean that these velocities would now decrease in length. The average velocity will be smaller. Do you agree? And then the other extreme, where again with this cold plate, I've got this big fan. Okay, and then what is going to happen now? Well, it is going to totally flow in that direction. So the natural convection, the buoyancy forces, is going to be so small that the forced convection, the inertial forces, are just dominant. Okay. Now the other type of flow, we've also looked at it, is maybe a heated sphere or a cylinder. If it is being heated, then the convection streams, flow path or streamlines would look like that. Okay. If there is no fan, if I put a small fan here, then it will force the flow direction a little bit more into that direction there. If I increase the fan size, I can actually force all the flow into that direction without the buoyancy forces playing any role. So that is a typical application of a flat plate. We have similar problems in laminar flow in tubes. So if that is our tube and the tube is being heated, let's suppose it is a case of a constant heat flux, and it is laminar flow. Okay. Then we have derived that for this case there's going to be a perfect parabolic velocity profile, and the Nusselt number is going to be 4.36. Do you remember? Well, this rarely happens. Okay. It is very difficult to repeat this experiment, because to do that you need very, very low heat fluxes. And if you've got very low heat fluxes, the temperature differences between the fluid and the wall becomes very small. Typically you get measurements of 0.3 degrees and less. And then only you can measure the heat transfer coefficients, so they are very small. So the result of these types of problems in practice is that if you look from this direction, and this is the tube, then because it is being heated, this wall, the density decreases and the flow wants to go up. And the result of that is that we get what is called secondary flow. It is actually symmetrical. My sketch is not so good, but typically something like that. Okay. So this is the buoyancy force that is being created. And the result of that is that in laminar flow, if you've got these types of flow, which is called mixed convection, MC for mixed convection, then the Nusselt numbers for laminar flow is in the order of approximately 10. So it's about double that of laminar flow only. Now in your textbook, only one paragraph is being considered on mixed convection. And you can write another textbook on its own on mixed convection. So you're just being introduced into the subject. And if you get this in industry, again, you will have to go and look at literature and get some more information. So in general, what you can have is the forces, which is, let's call it first, the inertia force, or the forced convection force, and we are going to consider that as an F. and then the buoyancy force. The buoyancy, which is B. So you can have different configurations in terms of these two different types of forces. So if we look at this first case, here we only have buoyancy force. Okay. In this case, we've got a buoyancy force and an inertia force, a forced convection. Okay. So it means that the first configuration is that you can have the inertial force, the forced convection force, and the buoyancy force working in the same direction. And then we call that assisting flow. And I think the name is obvious. They assist each other, they work together. Then the other possible configuration is that the inertial force and the buoyancy force are in opposite directions. What is an example of this one? Here it is. Do you see? The buoyancy goes up and the forced convection goes up, the inertial force. So this is called opposing flow. Again, very easy to see why it is called opposing flow. And the third category is transverse. So that would typically the buoyancy force in that direction and the inertial force in that direction. Okay, so transverse. And you'll see in the textbook that they are being described. Not as I'm doing here, I'm just doing it more schematically. But those are the principles. So the question now is that it's all good and well that we know about this, but the question is, when does it occur? When will I know which one occurs? Is it forced convection? Is it mixed convection? Or is it only natural convection? Well, for that we have to go back to what we did with the derivation of the momentum equation. And I'm just going to repeat it to you again. So it is the momentum equation, and it is equation 9.15 in your textbook. And this equation looks like this. U star multiplied by du star dx star. Now what is this, these stars? It's just non-dimensionalized distances, directions. Okay, plus other terms. I'm not going to put all of them in there. But at the stage, we get to a term which is equal to g multiplied by beta multiplied by Ts minus T infinite divided by the kinematic viscosity, something like that. And then there's a T there, and then there's a Reynolds number square there. Plus other terms. I'm not going to write them all down. But what is important in this is that we have introduced in the momentum equation the buoyancy effects, which was previously neglected in chapter, I don't know, 3, 4, or 5, or wherever where it was derived. Chapter 6. Okay. So what is important here is to look at the fact that this is the Grashof number and there's the Reynolds number square. So this ratio of the Grashof number divided by the Reynolds square is the driving force behind these different phenomena that we can get. And people did go and do experiments. So typically for a flat plate, they looked at the vertical plate, they've looked at the Grashof number divided by the Reynolds number square. Okay, so this variable here. And at the Nusselt number. Okay, and they did some experiments for all these different types of configurations. And for one or the other reason, I'm not really sure why, but it was easier for them to plot it on this axis there as Nusselt divided by Reynolds to the half. So they've just non-dimensionalized it. And then what they did is they've plotted it for different Prandtl numbers. And what they have found is the following. So this is for a Prandtl number of 0.03, and this is for a Prandtl number of approximately 1, and that was for a Prandtl number of approximately 100. And what they've noticed is that if they look at this, and then that is equal to 0.1, okay, and that is equal to 10. And they've noticed two very important things. Firstly, in this first region, where this ratio is smaller than 0.1, all the results remains constant. Okay? And in this region, all the results were the same as for turbulent flow. So if you look at it and you look at it carefully and you do lots of experiments, then based on that, they've suggested, well, that is actually now very easy. So what we can do is we can say, let's look at this ratio of the Grashof divided by the by Reynolds number squared. And if that is equal to 0.1 and that is equal to 10, let's categorize all the data. Okay. And what they have found is that in this part, the Nusselt number, which should be a function of the Reynolds, the Prandtl, and the Grashof number, okay, in this part, it's not a function of the Reynolds number. Okay? In this part, where the Nusselt number is a function, should be a function of Reynolds, Prandtl, and Grashof, they have found that the results are not dependent on the Grashof number. Okay? So, this is the natural convection part. And this part is forced convection. And guess what? That part is then named mixed convection. Okay, so mixed convection. And where we've got mixed convection, the Nusselt number is now a function of Reynolds, Prandtl, and Grashof, all three. Okay, so the mixed convection, also in this textbook, in this paragraph called combined convection. Does that make sense, ladies and gentlemen? Okay. So once they've discovered that, they have found something else which is important. So they said, well, this is great that we know that, but we still want to know how can I go and estimate the Nusselt number for a case like this, especially if we've got data for forced convection only and data for natural convection only. And after they've experimented a little bit, they have found that, well, that is actually very easy. What they have found is to say that the Nusselt number for combined convection or mixed convection, as I would prefer to call it, combined convection or mixed convection, is equal to the Nusselt number for forced convection to the n plus the Nusselt number for natural convection to the n, everything to the 1 divided by n. Where for a flat plate, n is approximately in the order of 3 to 4. Okay. However, there's one thing that still needs to be modified here, and that is that this is actually plus or minus. Plus or minus. Now, what do I mean with plus or minus? It means that in the one case, you have to add the two, and in the other case, you have to subtract it. And guess what? If we now look at these definitions, if they assist, they must be plus. If they oppose, it must be negative. If it is transverse, it must be positive. So it's as easy as that. So let's just write it down for in case you are not sure. So if it is assisting flow, if it's assisting, then the Nusselt number for mixed convection is then equal to the Nusselt number for forced convection to the n plus Nusselt for natural convection to the n to the 1 divided by n. And this is not only for assisting flow but also for transverse flow. For those two cases, assisting flow and transverse flow, then the sign there is plus. For the cases where it is opposing flow, then the Nusselt number for mixed convection, MC, just mixed convection, is equal to the Nusselt number of forced convection to the n minus the Nusselt number for mixed convection to the n to the 1 divided by n. So in that case, the sign is negative. Any questions on the theory part of mixed convection before we do an example? Nothing? Okay. So let's do an example. The example is going to be a flat plate. Flat plate, 0.2 meters by 0.2 meters. And it's in a vertical position. The flat plate is being heated to 40 degrees Celsius. And we have a velocity of a fan of 0.4 meters per second blowing over the flat plate in an upward direction, while TF, or not TF, T environment, the ambient temperature is 20 degrees Celsius. Okay, so flat plate, like this, in a vertical position, it's being heated to 40 degrees Celsius. Dimensions 0.2 meters by 0.2 meters, velocity of 0.4 meters from below in an upward direction. And the question is to determine the heat transfer rate for, firstly, the case where the velocity is an upward direction and then in a downward direction of 0.4 meters per second. So two different possibilities for the fan. Right. We have done flat plates many times. We know that we need the film temperature to get the properties, so let's do that quickly. The film temperature would be 20 plus 40 is 60 divided by 2 is 30 degrees Celsius. You agree? So the film temperature is just the average of 40 plus 20 divided by 2 is 30 degrees Celsius. So at 30 degrees Celsius, the thermal conductivity of the air is equal to 0.025 88 watts per meter Kelvin. Beta is equal to 1 divided by TF, and that is 1 divided by 273 plus 30, so it is 1 divided by 303. And the kinematic viscosity is 1.608 multiplied by 10 to the minus 5 square meters per second. Let's calculate the Reynolds number. The Reynolds number is equal to the velocity multiplied by characteristic length divided by the viscosity, the kinematic viscosity. The velocity is 0.4. It doesn't matter if it's going up or down. The characteristic length is the length of the plate, which is 200 millimeters, divided by the kinematic viscosity, which is equal to 1.608 multiplied by 10 to the minus 5. And the result of that is a Reynolds number of 4,975. Is it laminar flow or turbulent flow? Not turbulent flow, because 2,300 is for tube, and this is a flat plate. So transition occurs there 10 to the 5 or something like that. So the flow is laminar for a flat plate. Let's calculate the Grashof number. Grashof number for a flat plate. If you look at the table, you'll see we have to base it on the length of the plate. It's equal to GB multiplied by TS minus T infinite L to the third divided by the kinematic viscosity square. G is equal to 9.81. Beta is 1 divided by 303. The wall temperature is 40 degrees. The environment temperature is 20. Very important thing is the characteristic length. If you go and look in your table, for a vertical plate like that, it is that distance there. Okay, if it's another type of plate, the characteristic length is being determined by the surface area divided by the perimeter. So in this case, it is easy. It is equal to 0.2 to the third divided by the kinematic viscosity is equal to 1.608 multiplied by 10 to the minus 5. Everything square. And the result is a Grashof number of 2 multiplied by 10 to the 7. So let's see if we now look at these definitions of when the flow is natural convection, mixed convection, or forced convection. Okay. Let's look at Grashof divided by Reynolds square. Okay, so if we take this value of 2 multiplied by 10 to the 7, divided by the Reynolds number 4975 square, and that is equal to 0.805. 0.805. So if we look at our scale of there's 0.1 and there's 10, we are now in the area of mixed convection. Do you agree? Okay, so we've got mixed convection. So if we've got mixed convection, now we have to determine the Nusselt number for forced convection, and then we have to determine the Nusselt number from the plate for natural convection. Okay, so let's do that. So the Nusselt number for natural convection, the Nusselt number for natural convection from a vertical plate, and I'm going to take the simple equation because I don't want to, because I'm a bit lazy, that's the reason. Rally to the fourth, and that is equation 919 in your textbook, if you don't know where it comes from. So just go and look in your textbook, you'll see based on that condition in terms of the Grashof number, we can use that equation for natural convection. Okay. Then, the equation for forced convection. For forced convection, you've done that already. That was when you did the chapter on external flow, and specifically the part over flat plates. And that equation gave the Nusselt number as 0.664 multiplied by Reynolds 0.5 multiplied by Prandtl to the third. And that was equation 721. So that was in chapter 7, external forced convection. Take note. In natural convection, we see the Nusselt number is only a function of Rayleigh number only. Forced convection, it's a function of Reynolds number. Okay. So there's a Rayleigh number, there's a Reynolds number, there's the Prandtl number. I'm sure I don't have to write it out for you. But if you go and calculate it now, then you can calculate the Nusselt number for natural convection is equal to 36.46, and the Nusselt number for forced convection is equal to 42.14. So we can also immediately see the values are approximately the same order of magnitude. The one is not 10 times or 100 times larger than the other one. So we've got two possibilities. The one is assisting flow, and the other case would be opposing flow. Okay. If that is a flat plate, okay, our buoyancy forces is going in that direction, and our forced convection is also going in that direction. Okay. Then the Nusselt number for mixed convection would then be equal to our Nusselt number for forced convection to the n plus our Nusselt number for natural convection to the n, everything 1 divided by n. And take note, there's a plus. In this case, the Nusselt number for mixed convection would be equal to the Nusselt number for forced convection, but now minus. So in that case, they are assisting each other. In this case, they are opposing each other. The Nusselt number for mixed convection to the n, and 1 divided by n. Right. So let's look at this one. The natural convection for forced convection is equal to 42.14. I'm going to use n as equal to 3. You can use 4 also. It is a judgment call. It will depend on many other factors, but we don't have time to go into that detail. Plus the Nusselt number for natural convection, which is 36.46, to the third, and everything 1 divided by 3. And the result is a Nusselt number of 49.18. In this case, it is equal to the forced convection value is 42.14 to the third minus 36.46 to the third, 1 divided by n. Okay. Now when I wrote this down, I was immediately worried that, I changed the order, maybe I made a mistake with the order. What happens now if the one is larger than the other? For example, let's suppose this one was 36 and that one was 42. Then you end up with a negative. Just JIPO them, doesn't matter. Okay, so always take the biggest one minus the smallest one. Right, so that one is then equal to 29.8 Nusselt number. You see the difference? This one about 50, that one about 30, because of the opposing flow direction. Right, the Nusselt number is equal to the heat transfer coefficient multiplied by characteristic length divided by K. For this one, the same, the Nusselt number is equal to the heat transfer coefficient multiplied by L divided by K. The Nusselt number is 49.18, is equal to the heat transfer coefficient, that is what we want to determine, multiplied by L, which is the characteristic length, divided by the thermal conductivity K, which is equal to 0.02588. And from that, we can get the heat transfer coefficient as 6.364 watts per square meter degree Celsius. Okay. Look at the value, about 6 makes sense. If it's 600, you must know you've made a mistake. If it's less than, oh, no, not this one, but that one, if it's less than 1, remember, it can't be. And again, I mean, here we can do exactly the same calculation and then get the heat transfer coefficient as equal to 3.856 watts per square meter degree Celsius. Okay. I don't have any more room on the board, but if you can just continue underneath these two columns, first the left-hand one, left-hand side, and then the right-hand side. If we look at the heat transfer rate, it's going to be equal to the heat transfer coefficient multiplied by the area, the temperature of the plate minus the ambient temperature. And here the same. The heat transfer coefficient multiplied by the area, the temperature of the plate minus the environment temperature. I see I've used TH there. So let's rather change this back to TH. There we go. Okay. And this heat transfer coefficient must, of course, be the heat transfer coefficient now of the natural convection. So if you want to, you can put in there an NC and an NC to indicate natural convection, the transfer coefficient of natural convection and natural convection. Sorry, mixed convection. Mixed convection, yes. Mixed convection, right. There you go. Okay. So the calculation on this side is equal to the heat transfer coefficient is equal to 6.366 multiplied by the surface area. The surface area is 0.2 multiplied by 0.2 multiplied by the temperature of the plate, which is 40 minus 20, and that gives us a heat transfer rate of 5 watts. 5.091 or 7 watts, something like that. Approximately 5 watts. And you can do the same calculation, or just look at the ratio of the two heat transfer coefficients, and then you can calculate the heat transfer rate on this side as 3 watts. Very small, but there they are. Ladies and gentlemen, any questions on mixed convection or combined convection? Nothing? That's the case. Thank you very much and enjoy the rest of your day.